We continue Module 6 with a look at the common ion effect and how it affects acid-base equilibria. As we're going to see, a lot of the systems that we're going to be focused on throughout this module are really going to involve an acid-base equilibrium of some kind, and these are also the ones that come up most prevalently in nature. So let's see what we can learn about this. Our goals for this lesson are to understand what factors can be used to affect an acid-base equilibrium. So what factors will actually shift that equilibrium one direction or the other to make a solution less or more acidic, for example. We're also going to look at how these effects come into bearing with a titration curve. And if you haven't done a titration before in a chemistry lab, this will be a chance to learn about it. But it's a very interesting technique, and we can learn an awful lot about acid-base systems by looking at titration curves. So we're going to start again with a weak base equilibrium, so an acid dissociation equilibrium, but I'm not going to specify an acid at this point. I'm just going to leave it very generic. So we're going to look at this generic equilibrium for a weak acid, HA, dissociating into A-, the conjugate base, and hydronium ions. Again, this is a weak acid, so its Ka value is going to be less than 1. Now, there are ways that we can manipulate the position of the equilibrium for this weak acid dissociation. We could add more of the undissociated weak acid, and then, according to Le Chatelier's principle, the equilibrium should shift away from the side where we added stuff, so it would shift to the right, and that would cause more H3O plus to appear in the solution, so it would make the solution more acidic. We could also add more of the conjugate base, A-, and that's on the right-hand side of the equation. So again, following Le Chatelier's principle, that would shift the equilibrium back to the left, which would in effect raise the pH because it would be depleting the solution of hydronium ions. We could also, of course, just add hydronium ions itself. The equilibrium will shift to the left in accord with Le Chatelier's principle, but it still lowers the pH. It still makes it more acidic because of what we've added to it, basically more H3O+. We could also affect this equilibrium by adding hydroxide ion. Now, what effect is that going to have? Well, it will effectively shift the equilibrium to the right, but it will raise the pH. So it will make the solution less acidic. Now, these are things, the last two especially, are things that may seem counterintuitive because the acidity of the solution actually opposes the direction in which the equilibrium is shifted, but it's because we're adding hydronium ion in a pure form or hydroxide ion that it causes these shifts to either raise the acidity or lower the acidity. Now, one of the things that we're going to be very interested in this lesson and in subsequent lessons are polyprotic acids. Now, polyprotic, what does that mean? Poly means many, protic means many protons. So a polyprotic acid is an acid that can donate multiple protons. Now, there are some very common inorganic examples. Carbonic acid is a diprotic acid. Sulfuric acid, a very strong acid, is also diprotic, and phosphoric acid is a triprotic acid. It has 3 protons that it can donate. Now, if we have a triprotic acid, and phosphoric acid is not the only one, but it is certainly the one that we see most often in chemistry classes, we're going to have 3 different acid dissociation processes. So you can imagine the original triprotic acid, H3A, dissociating to form H2A- and hydronium ion, and that's going to have a particular Ka value, and we're going to call that Ka1. It's the first proton to dissociate from the acid, and because it's a weak acid, it'll be less than 1. Now, that H2A- still has 2 acidic protons on it, and so it too can undergo an acid dissociation equilibrium, and this is in the second chemical equation written there. So H2A- can react with water to form Ha2-, so doubly negative charged, and hydronium ion. And this too will have a Ka value because it's a standard acid dissociation equilibrium. We'll call that Ka2, and it is generally true that Ka2 will be less than Ka1. So this is becoming each successive proton that we're removing from the polyprotic acid, is less acidic than the previous one. Finally, this one has a third proton it can donate, so Ha2- can react with water to form the bare conjugate base A3- and hydronium ion, and it too will have a Ka value, Ka3, which will in general be less than Ka2. So we have three different Ka values that accrue because we have a triprotic acid. And in general, the number of Ka values that one could potentially measure is equal to the number of acidic protons that might be in the polyprotic acid. Now let's look at an example just to illustrate what we're talking about. Look at the first compound on the upper left there. So it's a benzene ring with an OH and an NH3 plus attached. So it's basically an amine that has been protonated. And so when we react that with water, we would find that it would react to form the amino compound, NH3 and OH attached to the benzene ring, and H3O plus. We could also look at a related compound, which is below, which is namely that first one, the product of the first reaction, and how it reacts with water, and it might lose the proton from the hydroxide, which is part of the alcohol, to form, again, the anion that's shown there, NH3O plus. So the question might be, if you were just considering these two compounds that are forming the reactants on the left side of both of these reactions, which of the protons would be most acidic? Well, if we recognize that, in fact, the second reaction is basically the first compound losing its second proton, that means that it really is the Ka2 of the first reaction. That is, the first reaction is going to lose two protons. The first one it loses seems to be from the NH3 plus part of the compound, and the second one comes from the OH part of the compound. So that would tell us that this first one, Ka1, is 1.66 times 10 to the minus fifth. That's still a weak acid, but it's a reasonably strong weak acid. The second one, however, is 10 to the fifth less strong. So the loss of the proton from the alcohol group on this organic compound is only about 1 times 10 to the minus 10. This, by the way, is fairly typical of aromatic rings attached to alcohol. So phenol, which is a benzene ring attached to OH, has about this same Ka value, about 1 times 10 to the minus 10. If you have an alcohol that's on just a regular hydrocarbon, a straight chain hydrocarbon, the Ka values tend to be around 10 to the minus 15, so they're much less acidic. So good example here to show us, what we can typically expect in terms of the acidity of different protons when there's more than one available on an organic compound. Now, oxalic acid is another great example of an organic compound that has two acidic protons. So oxalic acid is the molecule drawn in the upper left side of this slide. And you'll see it's actually a very interesting symmetric sort of molecule. It has two protons, both of which are acidic. And so as it undergoes its first acid dissociation with water, it will lose one of those. It doesn't matter which one, they're both the same. But it'll lose one of those to form the anion, which is the conjugate base for oxalic acid, plus hydronium ion. And that has a Ka value of 5.89 times 10 to the minus 2. It then will subsequently lose the second proton, and now that proton is, the first one on the left, and it forms the oxalate ion C2O4 2- plus hydronium ion, and that has a Ka value of 6.46 times 10 to the minus fifth. So it's 1,000 times less acidic. Nevertheless, it's still a reasonably good weak acid. So what we see from this is that even though those two protons were essentially identical in the original compound, once we've taken one of them off, it becomes more difficult to remove the second one. All right, part of that is because the compound now has an overall negative charge, so it's harder to pull a positive charge away from that negative charge. That was not true in the original neutral compound, so we were able to lose that proton fairly readily. All right, so again, we see good reasoning for successive acid dissociation constants becoming weaker, So that means the protons that are being drawn off are less acidic with each successive one that we take. Now, let's suppose that we want to take this and determine what the pH value would be for oxalic acid in an aqueous solution. So we're going to start with a 0.1 molar oxalic acid solution, and we need to figure out what the hydronium ion concentration is. So that's what we'll set our variable x to be. Now, if we write out the equilibrium expression for Ka1, that's going to be the hydrogen oxalate ion times the hydronium ion divided by the original oxalic acid concentration. And it's just a standard equilibrium problem that we're going to solve here. The concentrations of both hydronium ion and the Hc2O4 minus ion are the same, and they're going to be x, so that's x squared in the numerator. And the oxalic acid, H2C2O4, starts off at 0.1 molar, and it loses a little bit, x, so its equilibrium concentration is going to be 0.1 minus x. And that's going to be equal to the equilibrium constant for the first dissociation, 0.0589. So if we just solve that equation for x, and we can use Wolfram alpha to do that, or if we're really keen to do that by hand, it also can be done. But we would then find that x, and therefore the hydronium ion concentration, is going to be 0.0528 molar, and the pH that's implied by that is 1.277 molar. So the question that we would like to figure out here now is, how is the acidity of this solution going to be affected by losing the second acidic proton? So let's go and solve the second equilibrium. So now I'm going to set up the ice table for the second dissociation, and we're using the oxalic acid that we had at the end of the first equilibrium, the Hc2O4 minus at the end of the first equilibrium, which is 0.0528, and that's the same for the hydronium ion. So those two start off as having the same concentration at the initial point for the second acid dissociation equilibrium. We're going to lose the second proton, so we're going to lose some amount, x, from the Hc2O4 minus ion. That is going to be added to the reserve that we have of hydronium ion already in solution, and we will also be creating some oxalate ion with no protons attached, the C2O4 2 minus. So now when we go down and add those two rows together to get our equilibrium row in the ice table, the concentration of Hc2O4 minus is 0.0528 minus x. The concentration of hydronium ion, H3O plus, is 0.0528 plus x. And the concentration of the oxalate ion, C2O4 2 minus, is x. So now when we plug those into the expression for Ka2, which is the equilibrium constant for that second acid dissociation, we're going to get the expression shown in the middle there. It looks pretty awful. Lots of x's in the numerator and the denominator. Probably isn't going to be much fun to solve by hand, but again, Wolfram alpha has no problem solving that problem for you. And we would find that x in this case is 0.0000646. And of course, that's equal to the oxalate ion. I mean, if we look at how it's defined in the table above, it is the amount of oxalate ion that's produced. It's also the amount of additional hydronium ion that is produced by the second acid dissociation. So let's take a look at how that affects the concentration of hydronium ion as a whole. The equilibrium concentration of hydronium ion, which is in the E line of the ice table, is 0.0528 plus x. The x is equal to 0.0000646, so when we add those two together, in fact, we'll end up with a final solution, final concentration of H3O plus of 0.0529 molar. So it really only increased by 0.0001 molar. So now the pH, instead of being 1.277, is 1.276. All right, I went through this example in detail simply to illustrate that even though the second acid dissociation equilibrium constant was about 1,000 times less than the first one, it still has a negligible effect on the amount of hydronium ion that's created. So most of the acidity for a polyprotic acid comes from the loss of the first proton. That's what generally sets the pH. It may shift a little bit due to subsequent protons being lost, but most of it is coming from the very first proton that's dissociated from the acid. Okay, let's talk a little bit about titration curves. Now, again, if you've had a chemistry lab before, you may have done a titration experiment. It's basically an analytical technique that is devised to help you determine how acidic an unknown solution might be. So typically what you would do is add an indicator that changes color when it becomes, when it goes from neutral to, or basic to acidic, or from acidic to basic rather, sorry. You drip a little bit of base in until things make that change and the color changes, and then you understand how much acid was in there to begin with. Now, a very typical sort of titration curve might be a strong acid, strong base titration. So, for example, we may have nitric acid, HNO3, to which we're going to add small amounts of NaOH, which is a strong base, and monitor the color change until it changes in a way that reassures us that the system has gone from being acidic to being slightly basic. Now, in aqueous solution, both of these are strong electrolytes, and that's why they're a strong acid and a strong base. So the HNO3 is going to completely dissociate, forming hydronium ions and nitrate ions, and the sodium hydroxide is going to completely dissociate to form sodium ions and hydroxide ions. Now, I want to be sure that we understand that all of the stuff that's happening here is really between the hydroxide ion and the hydronium ion. The sodium and the nitrate, they're purely spectator ions. They do not participate in the chemistry of this titration. So our net reaction is simply going to be H3O plus OH minus, hydronium ion plus hydroxide ion, making undissociated water. Now, you'll notice that this is actually the reverse direction of the normal water autoionization reaction. So it has an equilibrium constant, and since it's the reverse of that reaction, the equilibrium constant is 1 over Kw, which is 10 to the 14th. Well, this tells you that this happens virtually completely. All of the hydroxide ions and hydronium ions that can react will react in this scenario. Now, what does this give you? It actually gives you, if you measure this at a bunch of different amounts of OH minus added, it gives you a curve that shows you how the acidity of the solution changed as you added the base. So let's get acquainted with what's on this curve. On the horizontal axis, we're measuring the amount of hydroxide ion that's added. On the vertical axis, we're measuring the pH. So in effect, pH of 7 is a neutral compound, and for a strong acid, strong base, that is also where we see the equivalence point, which is the point at which the amount of base that we've added is exactly equal to the amount of acid that was in the original solution. All right, now this curve will continue. As we continue to add base, it will continue to get higher and higher pH because we're now turning it into a basic solution. But it doesn't actually get to 14. It approaches it asymptotically, which means it approaches it gradually, but never quite gets there. But 14 is going to be the upper limit, if you will, for this kind of titration. Now let's think about the progress of the titration, see if we can understand why the curve has this interesting shape. And this shape, by the way, is very typical of a strong acid, strong base titration. In other words, it always looks like this kind of flat S. The equivalence point, which is midway up the vertical branch of this flat S, is always at a pH of 7 for a strong acid, strong base titration. But let's see if we can understand how the curve changes as we add the base. Now, I need to remind you that pH is a logarithmic scale. So if I change the pH by 1 unit, that's changing the concentration of the hydronium ion by a factor of 10, and that's part of what contributes to the shape of this curve. So let's suppose that we get to the halfway point. So we're halfway across the horizontal axis between the left-hand side and where the dashed line is that leads up to the equivalence point. And you can see at the halfway point there, the pH really isn't a whole lot different from what it was at the beginning of the titration, which is the point where it is on the left axis, on the vertical axis. So at that halfway point, basically the amount of base that we've added is half the amount of the hydronium ion that was present in the original solution. I call that H3O plus with a subscript 0 to indicate that it's the initial concentration of the H3O plus. Now, since we've only changed the constant, we've neutralized half of the acid, so only half of the acid remains. We've only changed the amount of acid by a factor of 2, and the net effect that this has on pH is to raise the pH by 0.3, so not a whole lot. It hasn't even been raised by a factor of 10. So let's go to the next point. So let's say now that we have added, we have as much base added as 90% of the acid that's there. So the amount of acid that remains is only 1/10 as much as we had in the original pure acid solution. Okay, since it's 1/10, that means the pH has gone up by 1. So even still, we've moved 90% of the way from the vertical axis over to the vertical dashed line, and we've only increased the pH by 1 unit on the way from whatever it started at to 7. If we go another 9%, so we're 99% of the way to the equivalence point, we've raised now the pH from the initial pH plus 2. So you can see that we're adding now less and less hydroxide ion. We're getting closer and closer to the equivalence point, but it's only going up by 1 unit in pH when we've added another 90% of what's left to the amount of the acid that was present. So this is what makes it such a steep rise up to the equivalence point. Basically, to be within 1 unit of the equivalence point, you're going to be at 0.9999 amount of base added to the acid. All right. So let's see what happens when we look at a weak acid titration with a strong base. Now, some of the things that are different are that the acid does not completely dissociate, and this has consequences for the way the titration curve is laid out. For one, the initial pH is going to depend not only on the concentration of the weak acid, but also on its acid dissociation constant, because that's what really sets the amount of hydronium ion that will appear in the solution. The strong base, OH-, mostly removes H+ from the weak acid, HA, that has not yet dissociated. Okay, if I write the equation for that reaction, I take OH- reacting with HA, both of those in aqueous solution, I'll get the conjugate base of the weak acid and water, and I can see from my mathematical equation below that for the equilibrium constant that the equilibrium constant is going to be the weak acid dissociation constant divided by the water autoionization constant. And since the water ionization constant is 10 to the minus 14, when I divide by that, I'm basically multiplying the weak acid dissociation by 10 to the 14, so it typically is going to be much greater than 1. All right, so this means that that reaction that I've shown, hydroxide ion plus HA, essentially goes to completion in most cases. So our procedure for finding the pH as we move across the weak acid titration curve is that we're going to actually be solving an equilibrium problem for the hydroxide ion. And we're going to be using that hydroxide ion concentration to obtain POH. But you may recall from Module 5 that we can relate POH, which is just minus log of the OH- concentration, we can relate that to the pH because the two of them added together have to equal 14 in an aqueous solution. So pH is going to be 14 minus the POH that we calculate from solving this equilibrium problem. What does this curve look like? Well, let's take a look. All right, here's an example of a weak acid titration curve, and we can see that there are a few things that are a little bit different about it, but it has an interesting shape. It tends to sit higher, at least in the early parts of the titration. It sits higher than the strong acid, strong base titration, and it has a equivalence point that actually lies above the equivalence point of neutral water. Let's talk about this in a little bit more depth. So I just mentioned that the initial pH is higher because the weak acid dissociation doesn't just immediately dissociate to form all hydronium ions, so it's going to start higher up on the vertical axis at the initial point. The shape of the curve at early stages, so this part here, which has also been labeled the buffer region, is very characteristically different for weak acids than from strong acid, strong base titrations. You'll notice, in fact, that it kind of puffs up a little bit, then it flattens out, and this characteristic shape is one that almost always tells you, yes, I've got a weak acid, not a strong acid being titrated in this. And I mentioned earlier the equivalence point is at a pH greater than 7, and that's, again, a manifestation of the fact that our weak acid doesn't fully dissociate in water. It has a equilibrium constant, and so that is going to cause a different different pH to occur when we've added as much base as we have weak acid in the solution. All right, so in effect, the equivalence point is a basic solution. It's got more base than acid, again, because of this weak acid situation. So what happens if we go to a polyprotic acid? Now, I'm showing you the curve right from the start because there's a lot of details of this curve that I want to point out. Okay, one, the initial pH is higher still. The first weak acid dissociation in a polyprotic acid typically is weaker than at least the one that I showed in the previous weak acid titration curve. The shape of the curve at early stages is very much like a weak acid titration. So we see it kind of initially puff up, but then flattens out, and then curves up again when it gets nearer to the first equivalence point. As we found in the weak acid titration, its first equivalence point is above 7, so it's above neutral water. But then it has a second flat region, a second buffer region, that then eventually goes up to a second equivalence point. All right, so this staircase profile is very typical of polyprotic acids. And in fact, if you've got good enough resolution on your polyprotic acid titration curve, you can even figure out how many different protons there are that are acidic in your weak acid. Okay, the second equivalence point, of course, is even higher still than the first equivalence point. But you can see that the two vertical blue lines, the vertical dashed blue lines, which mark the equivalence points, are equally spaced from the vertical axis. So the same amount of base that it took to to get to the first equivalence point, you're adding that same amount of base to get to the second equivalence point. If we had a triprotic acid, there would be a third step in this profile. I will say that having looked at a couple of multiple or polyprotic acid titration curves, it's really hard to distinguish more than about 2 acidic protons when you look at these curves. But it is a very characteristic shape and one that you should look out for. So I hope in this lesson you've learned what factors can be used to shift the equilibrium of a weak acid, and how that influences the acidity or basicity of a given solution. We've seen that there are several things that we can learn from just looking at a titration curve. We can tell if we've got a strong acid or a weak acid. We can tell if we have a monoprotic or a polyprotic acid also by looking at that. So there are some very clear signposts that we can look for as we look at titration curves. We'll learn more about these as we move on through this module. Thank you.